Hello and welcome to Lecture 52 of my class From Data to Decisions. I'm Chris Mack, your instructor for this course. In this lecture, we'll visit the topics of the previous two lectures in R. We'll look at how to detect multicollinearity, and then we'll look at one of the ways of addressing multicollinearity, bridge regression. All right, let's start with detecting multicollinearity. A few lectures back, we talked about this. We talked about how to do it in R using one technique, the correlation matrix. So I'm going to load up a data set that we've talked about many times before. Here's a plot showing the output, body fat percentage, and then the inputs, the regressive variables, weight, chest, abdomen, hip, thigh, and biceps, all these measurements. And we want to build a model to predict the percent body fat. You see that some of these regressive variables are highly correlated with each other. And we can quantify that with this correlation matrix. So if I look at it, I see all the correlations both with the response variable body fat, but also between regressive variables. The correlation matrix is somewhat limited because it's only pairwise correlations. It shows how one variable correlates with a second variable. Sometimes correlations can be more complicated. So we talked about two other ways of understanding the level of multicollinearity for more complicated correlations, not just pairwise. And one of those techniques was Eigen system analysis. And there's a function called Eigen, and I will apply that function to the correlation matrix. Our Eigen system analysis, we want to do it on the correlation matrix itself because then we have all of the centered and scaled versions of the correlations, and we can look at a bigger picture of how each variable correlates with all the other variables, not just pairwise. So Eigen will calculate the eigenvalues and the eigenvectors, but we only need the values here, so I will simply run that, and I see a list of eigenvalues, one for each predictor variable. If all the eigenvalues are about the same in magnitude, then we don't have much multicollinearity. If the eigenvalues vary in magnitude from large to small, then we do. And that's what we see here. They're ordered in magnitude. 5.5 is the biggest one. 0.05 is the smallest one. So that's quite a range. In fact, we can quantify a range of eigenvalues using what's called the condition number. This is simply the ratio of the maximum to the minimum eigenvalues. So I calculate that ratio by taking the max of all the eigenvalues divided by the min of all the eigenvalues. And if I calculate, I see the value is 120. Our rule of thumb was if the value is on the order of 100 or more, then we have a significant multicollinearity problem with this data set. Notice that this could be true even if all of the pairwise correlation coefficients are not that concerning. We can also calculate this condition number, which is sometimes called kappa, with a specific function called kappa. Kappa is specifically calculating the condition number. We give it the same thing, the correlation matrix of the body fat. It has both exact and approximate methods of calculating kappa, so we want to set exact equal to true, not the default. So we need to explicitly set it if we want to calculate the actual value. And if I run that, same number, 120. So I can either look at the eigenvalues directly, or I can simply use this kappa function. What I think is probably the most useful way of detecting multicollinearity is with the variance inflation factors. All right, to do that, we have to first perform our linear regression. Then we look for the inflation, or the increase in the variance for a particular variable that comes about because of the correlation of that variable with the other predictor variables. So here I will use my data, and I'll use the period nomenclature that says I want body fat as a function of everything, linear with every single variable. I run that. I've done my linear regression now. What I'll do next is apply this function called VIF. VIF is in the car library. So I load the car library, which I've installed many times before, earlier. And then I simply do VIF of the model. If I run VIF of the model, it gives me the variance inflation factors for each of the predictor variables in the model. We see for weight, it's 13.8. For chest, it's 8.4. Abdomen, 7. Hip, 11. Thigh, 5. And biceps, 2. All of them are bigger than 1. Right? 1 means there's no variance inflation whatsoever. Our rules of thumb were variance inflation factor is 4 or larger. We worry about it. We think about it. We look at it. But variance inflation factor of 4 means the standard error for the confidence intervals around the coefficient for that term in the model will be twice as big as they would be otherwise. So that's why it's kind of a rule of thumb we've picked. We also say if variance inflation factor is bigger than 10, then we probably have to do something about it, not just think about it, not just worry about it, but actually do something. And you see a couple of variables where it's bigger than 10. The other thing we sometimes look at is the mean value of the variance inflation factor for all of the different terms. And if it's much bigger than 1 or 2, then we start worrying about it as well. And sure enough, this is 8. So I think with this data set, it's pretty clear we have a lot of multicollinearity. All of the techniques will tell us the same thing in this case because all of our multicollinearity for this data set is about pairwise. All right, so we've detected multicollinearity. What can we do about it? One technique we talked about was the ridge regression. I guess in some circumstances, the ridge regression is quite valuable. I have not found it to be useful in many of the things that I've done, but we'll look at it anyways. In particular, I'll give you kind of a synthetic example, a made-up example, which really demonstrates the power of the ridge regression. Here's what I'll do. I'm going to create 2 dummy variables. The first one, created by this command, is a set of random numbers, 20 of them, using the rnorm function. I don't supply mean or standard deviation, so the defaults are a mean of 0, standard deviation of 1. So I've now created 20 random numbers with a mean of 0, standard deviation of 1. Now I'm going to create another set of 20 random numbers, but this time I'll let the mean equal x1. So I'll give it the array of 20 numbers, and for each of the new random numbers x2 I generate, it will be a random number around that mean of x1, but I'll make the standard deviation 0.01, very, very small. In other words, x2 is almost the same as x1. Right? Not quite. If I go look at these numbers really quickly, you see that the first x1 is 2.233, the second x1 is 2.216. The next one's minus 0.716, the next one is x2 is minus 0.719. They're not exactly the same, but they are highly correlated with each other because of the nature of the way I generated them. How correlated? Let's look. We'll look at it. 0.99995. Right? 4 nines. That's a huge level of correlation. If you detected that level of pairwise correlation, you'd simply say I only need one of these 2 variables in my model. All right, but we're gonna do the ridge regression on this case anyways, because who knows, you might get really high levels of correlation without having pairwise correlation. All right, now I'm gonna create the response variable, and for the response variable, I'm going to use a model that is 3 plus x1 plus x2. So we know the true values of our coefficients. The intercept is 3. The coefficient of x1 is 1. The coefficient of x2 is 1. Because I know what the answer is, I can check how well my regression predicts these coefficients. And then I'll add an error term, which is simply a standard deviation of 0.2, normally distributed about the y value. All right, so to do that, now I have two x's and a y. I'll do linear regression. My model will be y as a function of x1 and x2. Let's do the regression. What do we get? Oh, well, the intercept is 3, about, not bad. Look at these two, x1 and x2. x1 is 1.7 and x2 is 0.17. They're supposed to be 1 and 1. We can see they're quite a bit off. You know, every time I run this, I can run it again, I get different values. Now my intercept is still about 3, but now look, x1 is minus 3.9 and x2 is 5.8. I run it again, x1 is 3.2 and x2 is minus 1.3. This is one of the effects of multicollinearity. If I create a different sample, if I go out and collect a different sample, but the variables are highly correlated, I'll get very, very different coefficients for my model. Even though nominally they are all generated by the same underlying physical phenomenon, the same equation governs, nonetheless with multicollinearity, there's a big difference. If you look here, you see that coefficients of x1 plus the coefficient of x2 is always about 2. And that's always going to be true here because of how highly correlated x1 and x2 are. And the true sum of the coefficients is 2. But I can't really tell how much is x1 and how much is x2. All right, now let's try ridge regression. Ridge regression is in this library called MASS. We've used it before, so I'll load that library. The thing about ridge regression is we need to know this constant. We're going to create a penalty function as a constant plus the sum of all the coefficients squared. Notice that the correct values of the coefficients are 1 and 1, but the incorrect values are numbers bigger than 1 and in this case smaller than minus 1. So if I summed the square of these two, I would get a number that's much bigger than 4, the number I get if I had the true values of 1 and 1. So I'm going to penalize the model for having coefficients that are too big, magnitude. To do that, I have to know a specific value of what I call k in my lecture, but what is called lambda in this particular nomenclature. We're going to run this program called lm.ridge. It's ridge linear modeling. It looks the same as our typical LM function. I'll give it the model y as a function of x1 plus x2. But I have to add an extra term, lambda equals. Okay? If I put lambda equal to 0, that means there's no penalty. And if I run that, I get the same coefficients for the fit as I did before let's see. I think I can get the coefficients by doing fit $coef. All right. So I will get the same coefficients, lambda equal to 0, as I got otherwise. If I run my LM, and then I run the ridge regression, don't get the same values. I don't know why. because I don't know what the value of this lambda is, the constant multiplying my penalty function for my ridge regression, I'm going to create a sequence of values, and I can go look through that sequence to find out which one is out the best. So I'll create LM underscore SEQ for Lambda sequence. It's a sequence that goes from 0 to 1 in steps of 0.001. I've got 1,001 lambda values. Now I'll run this Airfit and give it this entire sequence of lambda values. So I'll get, in fact, 1,001 ridge regressions. All right, it ran 1,001 ridge regressions. Now what? Now we need to look through all of these regression results and pick the best value of lambda, the best value of the constant multiplying by the penalty function. So there's another function called select that helps me pick it. And select looks at the generalized cross-validation. I haven't talked about cross-validation yet in the class, but very briefly, I take a percentage of the data points out, I do a fit without those, and I compare the fit predictions to the data points that I didn't use and see how well it fits those values, how well it matches those values. And I'll do this a whole bunch of times, randomly selecting, say, about 20% of the data for my cross-validation. And then the value of K, the value of lambda, the constant multiplying penalty function, which produces the best overall match to the cross-validation data, will be the one that I call the best. And so select looks at the smallest value of the generalized cross-validation. It says it's 0.062. Okay? So I'll put in 0.062 for my ridge regression. And this will be the ridge regression that will produce the best results. About. Right? So now I run this ridge regression, and it tells me the intercept is 3, and the coefficients are 0.99 and 0.9. Well, we know true values, said the intercept is 2.9. The true value is 3, 1, and 1. This is a lot closer than what we got when I did my OLS. So here's the OLS values. Right? It's about the same for the intercept, but quite a bit different for the two coefficients. Notice that the coefficients are both a little bit less than 1. Remember, it's pushing these coefficients to be smaller than they would be otherwise because of the penalty function. And that's what allows me to break the multicollinearity, but it is biasing my coefficients. We don't want to go too high in our value of lambda. Notice if I change the value of lambda 5, it changes those numbers a little bit. If I did 0.1, numbers are changed a little bit as well. So, but they're not changing a lot, and they're all a lot closer to the true values than we got with our ordinary least squares regression. Now, this is an example where ridge regression works at its best because the correlation between these two variables is so extremely high that even a little bit of nudge, a little bit of penalty is enough to get me much closer to the true values. And without this penalty, we can't even get anywhere close to true values. Well, in a lot of cases, it's not nearly this extreme. So most regression, we don't have such clear correlation, such clear extreme multicollinearity, and therefore ridge regression will not show such dramatic changes and dramatic results. Let's look at our body fat data and see. All right, I'll use the exact same body fat data that we did before, but this time I'll scale it. The reason you need to scale before you do a ridge regression, because I'm summing the squares of the coefficients. And unless I have scaled variables, I can't relate one coefficient of a model term to another coefficient of a model term. Right? If If they all have different units, how do I sum the squares of these coefficients? Only if they're normalized, only if they're standardized, am I allowed to properly sum up the squares of the coefficients and get a number that's meaningful. So in my previous fake example, both of my data had mean of 0 and standard deviation of 1, so they were standardized to begin with. So I didn't need to do that. With our body fat data, not standardized, all different measures with all different units and scales, standardization before I can do a ridge regression. Right, we've already looked at correlation matrix and variance inflation factors and eigenvalue ratio kappa. Now let's try ridge regression on this data. So again, I'll create a sequence and I'll run my fit to that sequence. One thing you could do, by the way, is you can plot the fit. If I do a plot of the fit, what I get is called the trace. I recall from the lecture, the trace is the values of each of the coefficients of the model as a function of lambda, as a function of this constant multiplying the penalty function. You can see all these values are getting smaller in magnitude, moving towards 0. We still have the problem of figuring out what is the best value, so we'll use this select function. And it actually has multiple estimates of where it says the best might be, but I like the smallest value of the generalized cross validation as my technique, and it says 0.81. If we want to, we can actually plot this generalized cross validation as a function of lambda. See that minimum is about here, 0.8, and either side it's larger. So we can run our ridge regression, lambda of 0.8, and I get a set of coefficients. Just as comparison, let's run that ridge regression with a lambda of 0. So I'm not penalizing for magnitudes of the coefficients. And you can see that in this case, the numbers aren't too very different. This is the intercept, the first number. It's about 0 because we've standardized our data. So with the standardized set of variables, the intercept is always going to be 0. But let's look at the coefficients. Here, the weight coefficient's 0.515. Here it's minus 0.537. So I changed a little bit. The other coefficients are changing a little bit, not very much. Is this a better? Are these better estimates? None of them changed particularly much. Maybe they're a little bit better. Because we don't have such extreme multicollinearity, the ridge regression is only causing small changes in the coefficients, and especially because we don't have a good exact number of what lambda should be. If I changed it a little bit lower, a little bit higher, I'm going to move these coefficients around again. Seems a little bit arbitrary. I'm not sure that ridge regression is the best approach to this data set. In coming couple of lectures, we'll talk about principal component analysis and principal component regression as maybe a more appropriate technique for this data set. Till then.